With an understanding of how to determine the frame size for the minimum side and for the maximum size, we investigated that and we are quite comfortable with that. Another important discussion is, should a network support variable length frames or fixed sized frames? In this module, we shall convince ourselves that why should we have fixed sized frames? And if we agree on fixed size frames, then what should be the appropriate size for that? The references that I've chosen are primarily the text and the figures are from Bertsicus and Gallagher. However, another interesting paper titled Optimal Fixed Frame Multiplexing in Integrated Line and Packet Switched Communication Networks by Basil Maglaris and Misha Schwartz. It's a classical paper published in 1982, is also of interest. So why should we have a fixed sized frame? Of course, the first thing that should intuitively strike our minds is we need to have the expectability of performance. We do not want our system to behave unexpectedly because the frames are of variable sizes. This expectability actually determines the overall application area of the network. For example, what is the typical latency observed in a network? What is the throughput and the cell loss? This also puts an expected requirement analysis for these parameters, how much should be the resource allotment. Some of the important considerations to determine a fixed size of the frame for a given network is, for longer frames, the processing for per frame is going to be less because the header would have a payload that is very, very large. So effectively, if we are representing a message in lesser number of frames, we are posing lesser load on the network resources. If we create too many frames, it actually means that each frame, which is shorter in size, would have its own header, and that header would be processed every time it passes through the nodes in the network. Another important consideration is, when we create a frame, what is the ratio of header to payload? Because if the payload is very small, we can accommodate a message in more number of frames, but the last frame is eventually going to have most probably some kind of padding requirement. But if we do this for longer frames, the padding requirement would be even more. So you can imagine that there's a trade-off between how many frames we can create and how much padding requirement we'd have for the last frame. Another important consideration is, what is the application area we are focusing on? For instance, if we are talking about voice and video, it's interactive. So for voice and video, the framing should be such that it achieves smaller delay. But is it equally applicable for large file transfers? In fact, it is not. For instance, if we assume that we have an arrival rate of R in terms of the bits, and the packet length is represented as K, the first bit in the packet is held up for K divided by R duration. Why? Because till the time the K sized frame or packet is created, the arrival would be allotted to that particular frame. So the first bit and subsequent bits would have to wait for that much time if the frame length is long. This is an important consideration because for interactive and real-time traffic, maybe such framing time is unaffordable. If we look at real-world networks, we observe that IP networks provide variable length. They provide a provision for a variable length. On the contrary, ATM recommends fixed cell size of 53 bytes with 48 bytes worth of payload and 5 bytes of header. 424 bits in terms of payload is a good representation of the mathematically determined optimal value of the frame size if real-time voice and video have to be serviced by the network. So ATM cell size is really good for interactive and audio-visual applications, but it certainly is not good for file transfer.